Hi everyone and welcome to our introduction to number theory and cryptography. In this lecture we will investigate together Euler's Dotion function, which we denoted for an integer m phi of m. Let me remind you that phi of m is equal to the number of elements of this set, all the a's which are between 1 and m minus 1, such that the GCD of a and m is equal to 1. We've also seen together that if the GCD of a and m is equal to 1, then we have Euler's theorem, which states that a powers phi of m is congruent to 1 modulo m. So in order to apply Euler's theorem every time, one needs to compute phi of m. For instance, if we would like to compute phi of 6, we will have to find all the elements a which are between 1 and 5, which is 6 minus 1, such that the GCD of a and 6 is equal to 1. Now we know that the GCD of 1 and 6 is equal to 1. The GCD of 2 and 6 is not equal to 1, so 2 is not part of this list. 3 is not part of the list too because the GCD of 3 and 6 is not equal to 1. 4 is not part of the list because the GCD of 4 and 6 is not equal to 1. And finally, 5 is part of the list because the GCD of 5 and 6 is equal to 1. So we find here that phi of 6 is equal to 2. We would like to find a systematic way to compute the function phi of m for every integer m. And of course, m will be taken greater than 2. In order to do this, we will prove some important facts about the function phi, and the first one is that phi of p with p is a prime number is equal to p minus 1. Second fact is that phi of p to the n is equal to p minus 1 times p powers n minus 1. And finally, and this is the most important thing about the function phi, is that if the GCD of m and n is equal to 1, then phi of m times n is equal to phi of m times phi of n. Why is this important and how is this going to be helpful for us? Well, it is all about the unique factorization theorem, which states that every integer n greater than 2 can be written in the unique way as n equals to p1 powers r1, p2 powers r2, until we get to pt powers rt, where actually p1, p2, and pt are distinct prime numbers. So from here we deduce if n is any integer greater than 2, then phi of n is equal to phi of p1 powers r1 times p2 powers r2 until we get to pt powers rt, and this is equal to phi of p1 powers r1 times phi of p2 powers r2 until we get to phi of pt powers rt. And actually this is because p1 r1 and p2 r2 are co-prime, so we used this one here to prove that this expression is equal to this one. Now from here we use the second proposition to get that this is equal to p minus 1, of course p1 minus 1 all times p1 powers r1 minus 1 times p2 minus 1 all times p2 powers r2 minus 1 until we get to pt minus 1 times pt powers rt minus 1. And actually this gives us a straight way to compute phi of n for every integer n greater than 2. Now before we prove our claims here, let us see how things work on a concrete example. If we take n is equal to 980, we see easily that n is equal to 2 squared times 5 times 7 squared. So from here we get that phi of 980 is equal to phi of 2 squared times 5 times 7 squared, and this is equal to phi of 2 squared times phi of 5 all times phi of 7 squared. And this is actually because 2 squared and 5 do not share any common divisor, except 1 of course, and it is the same thing with 7 squared. So from here to compute phi of 2 squared, we use our second proposition, and it says that it is equal to 2 minus 1 times 2 powers 2 minus 1. Phi of 5 is equal to p minus 1 because 5 is a prime number, so this is equal to 5 minus 1, and 5 7 squared is equal to 7 minus 1 all times 7 powers 2 minus 1, and we get from here that this is equal to 2 times 4 times 6 times 7, which is equal to 336. Bingo! So what we see here is that this is a very good way to compute phi of rather big numbers. Before we move on to the proofs of these claims, let us first go on Python to computer program a function that will compute phi of n and try to see experimentally whether these really work or not. So here we are on Python. I wrote two little computer programs. The first one is GCD GCD of a and b, which computes the GCD of two numbers a and b. Our second function is the function phi, which will compute for us phi of m, and here it checks whether the GCD of m and j is equal to 1, and if it is, it adds 1 to I. Now if we try our function phi with a prime number p, for instance, if we would like to compute phi of 7, we should find p minus 1, which is 6. Is this true? Actually, it is, with 7. Let us try phi of 17, for instance. Phi of 17 should be 16, and this is also true. Phi of 2, for instance, phi of 2 is equal to 1, and phi of 980, our number that we checked together, bingo, 336, which we found with the properties of phi. Now if we check for phi of 7 squared, which is 49, we should get 7 minus 1 times 7 powers 2 minus 1, which is 6 times 7, meaning 42. Is this true? Yes, it is. Now if you check for phi of 15, this is what we get, 8, and 8 is actually phi of 3 times phi of 5, because phi of 15 actually is phi of 5 times 3, and by our third property, we know that phi of 5 times 3 is phi of 5 times phi of 3. Phi of 5 is equal to 4, phi of 3 is equal to 2, because it is 3 minus 1, and 3 is a prime number, so we get 4 times 2, which is actually 8. Of course, our program here does not use the properties of the function phi to compute phi of m, but it helps us see that these properties hold for every integer m. I of course suggest you computer program these functions and try by yourself some values of phi to see that our three properties hold. I claim that the two first are trivial facts, but actually the third one, which is the most important one probably, is a little bit more subtle, and we will need the Chinese remainder theorem in order to prove it. So for the first property, if p is a prime number, then phi of p is equal to p minus 1, and this is actually easy to prove because the integers a between 1 and p minus 1 are all co-prime with p. They cannot share a divisor with p unless it is equal to 1. Hence, we know that the GCD of a and p will all the time be equal to 1, and since there are p minus 1 elements here, we get that phi of p is equal to p minus 1. Our second claim says that if p is a prime number, then phi of p to the n, where of course n is an integer greater than 1, is equal to p minus 1 all times p to the n minus 1. To figure out why, let us count actually the a's such that a is greater than 1 and lesser than p to the n that share a divisor actually with p to the n. If a shares a divisor with p to the n, then a must be of the form p times a certain integer t, right? Because all the divisors of p to the n are of the form p to the r, for r of course lesser than n. So from these inequalities we get that p times t is lesser than p to the n and greater than 1, which means that t itself actually is greater than 1 and lesser than p to the n minus 1. So in total, there are p to the n minus 1 numbers a of this form that share a divisor with p to the n, which means that phi of p to the n, meaning the number of numbers a that do not share any divisor with p to the n, is actually p to the n minus p to the n minus 1. Do you see why? This is because actually the total numbers of a is p to the n here, so this is our p to the n, from which we subtract the number of numbers that share a common divisor with p to the n. So we get p to the n minus p to the n minus 1, which is by factorization gives p to the n minus 1 all factor p minus 1. Hence our desired result. Let us now prove our third claim, which states that if the GCD of m and n is equal to 1, then we have that phi of m times n is equal to phi of m times phi of n. We know that phi of m is the number of co-prime elements with m, of course lesser than m, and phi of n is the number of co-prime elements with n lesser than n. So this suggests that we can construct the co-primes modulo mn using the co-primes modulo m and the co-primes modulo n. Notice first that phi of m times phi of n is the cardinal, actually the number of elements of the couples ui vj, where actually the GCD of ui and m is equal to 1, meaning that ui is co-prime with m, and we take vj co-prime with n. So, and the GCD of Vj and n is equal to 1, right? This holds easily because if you have two sets, E and F, then E product F is the set of x, y, where x is in E and y is in F, and the number of elements of this set here is simply the number of elements of E times the number of elements of F. And this is what I used here. We know that the numbers of coprime numbers with m is phi of m, and the number of coprime numbers with n is phi of n. And so if you take the set of all the couples, then the number of elements of this set is phi of m times phi of n. What we would like to show now is that to each couple here, there corresponds a unique element modulo mn here, which is coprime with mn. If you can do this, it will mean that phi of mn is equal to phi of m times phi of n. But how? Indeed, the Chinese remainder theorem says that this system, A is congruent to ui modulo m and A is congruent to Vj modulo n, has a unique solution A modulo mn. So all we have to do now is to show that A must be coprime with mn. And I'll leave it to you as a small exercise to show that the GCD of A and m times n is equal to 1 if and only if the GCD of A and n is equal to 1 and the GCD of A and m is equal to 1. Meaning that actually A is coprime with mn if and only if A is coprime with n and A is coprime with m. Of course, here m and n are coprime. Let us now apply Euler's theorem to an amusing example. We would like to find the three first digits of the number 2021 powers 2001. This is a huge number, so we will not do the computations to figure out the three first digits, but it is actually sufficient to know to which number this number is congruent modulo 1000. Okay? If you can compute the number a here, then we know that the first three digits of this number here will be the number a. Okay, so first we know that 2021 is congruent to 21 modulo 1000, and we know that 21 and 1000 are coprime. They do not share any common divisor because the prime divisors of 21 are 3 and 7, while the prime divisors of 1000 are 2 and 5. Hence, one can apply Euler's theorem, which states that 2021 all powers phi of 1000 is congruent to 1 modulo 1000. Correct? Now all we have to do is to compute phi 1000, and we know that 1000 is equal to 2 cubed times 5 cubed, which yields that phi of 1000 is equal to phi of 2 cubed times phi of 5 cubed, which gives actually by the properties of phi that this is equal to 2 minus 1 times 2 squared times 5 minus 1 times 5 squared, which is equal to 400. Great, so this means that 2021 powers 400 will be congruent to 1 modulo 1000. Now we know from here that 2001 is equal to 400 times 5 plus 1, which gives actually that 2021 powers 2001 is congruent to 2021 powers 400 times 5 plus 1, of course modulo 1000, and this is congruent to 2021 powers 400 all powers 5 times 2021 modulo, of course, 1000 still. This here gives us 1 modulo 1000, and this is due to Euler's theorem. So we get here that this is congruent to 2021 modulo 1000, which is congruent actually to 021 modulo 1000. And this actually says that the three first digits of our number here that we did not compute because it's too big are actually 0, 2, and 1. Very nice. Do you see how powerful Euler's theorem is? Our lecture ends here. Thank you for listening.